Okay, so in this video we're going to look at the fundamental set of solutions and the Wronskian. So for this section, this applies to second order linear homogeneous equations, right? And we know that because it needs to be in this form where it equals 0. That tells us that it is homogeneous. And it's second order because of this, right? So we know it's second order homogeneous. So for fundamental set of solutions, right? There's generally four steps for solving these kind of problems. So the first step is we're going to have to find two different solutions, y1 and y2, by proposing x equals e to the rt. By the way, for these kind of problems, it'll specifically ask you, like it'll say like verify like what y1 and y2 are solutions. Do they constitute a fundamental set of solutions? Like it'll ask that. So like it'll ask you to like find the fundamental set of solutions, right? So that's your key to use this technique here. So right, so we're gonna do that first. You should be familiar with this somewhat from the last section. But then for step 2, we're gonna verify that y1 and y2 are a fundamental set of solutions by taking the Wronskian. Number 3, we're going to write down a general solution. And then step 4, we're going to solve the IVP. Now for these questions, there's always going to be an initial value problem. And I'll show you what I mean by that in a second. Because we're either given conditions or we have to use a theorem which basically states theorems, which states that we have an IVP like always. So I'll show that I'll do a few examples that shows both cases. First, what I'm gonna do it when it gives us an IVP. So our first example, I'm gonna do a full out example, and then I'm gonna start small and work our way up through easier examples where it already gives us like y1 and y2. Oh my god. Where it already gives us y1 and y2, and we just have to determine if it's a fundamental set of solutions. All we have to do is take the Wronskian. But I'll show you how this all goes. So I'll do an example and full method. So example and method. So step 1, find two different solutions, y1 and y2, by proposing x. Oh, I forgot to write down the problem. So the problem is x double prime plus 7x prime plus 12x is equal to 0. So step 1, find two different solutions, y1 and y2, by proposing x equals e to the rt, right? This is the exact same thing we did in the last video. Right? So now if we plug those back into our equation here, that's r squared e to the rt plus 7 times r e to the rt plus 12 e to the rt. These cancel. And don't forget, equals 0. So we have r squared plus 7r plus 12. This can factor out very nicely. R plus 3 times r plus 4, yep, is equal to 0. So then r is equal to negative 3. R is equal to negative 4. So then we have our two solutions. So y1 is e to the negative 3t, and y2 is e to the negative 4t. So now, really quick, let me go over the Wronskian. So the Wronskian would take y1, so the Wronskian of y1 and y2 is going to look like it's going to be the determinant of y1, y1, y2, y1 prime, y2 prime, which can be rewritten as, this is just a straight straight bar here. y1, y2. This is the symbol for determinant. y1 prime, y2 prime. Now this looks like, if we were to do the determinant, you do this row first, and then you do this one. So it starts with y1 times y2, you multiply them, y1 times y2, and then you subtract this one. So then that's y2 minus y2 times y1 prime. And then if the Wronskian of y1, y2 is non-zero, then we have a fundamental set of solutions. Okay, so let's try it for this one now. So if we take the Wronskian of e to the negative 3t and e to the negative 4t, then we're taking the determinant of y1, so we just rewrite these two on the top here. And then we take the derivative of them right under here. So the derivative of e to the negative 3t is negative 3e to the negative 3t. And this one would be negative 4e to the negative 4t. Now we take the determinant of that. So that's e to the negative 3t times negative 4e to the minus 4t, right? We go this way first. We go this way. So then we have, that's negative 4e. What's negative 4 minus 3? It's negative 7t. And then we're going to subtract this one this way, right? So that's e to the negative 4t. So that's, minus e to the negative 4t times negative 3. So because we have that negative there, this becomes positive. And then we have e to the negative 4t. So then that's plus 3. Negative 3 minus 4 is also negative 7t. And then that's going to simplify to negative 4 plus 3 is negative 1, right? That's negative e to the negative 7t. And this is non-zero, right? So we have a fundamental set of solutions. So that was step 2 right there, right? This was step 2. We verified that y1 and y2 is a fundamental set of solutions. So now step 3, we're going to write the general solution. So now that we've verified it's a fundamental set of solutions, we can go ahead and write out our general solution. Now this is just like the last video. We're going to have C1, what's y1 again? E to the negative 3t plus C2, y2 was e to the negative 4t. Right, the general solution, the general form, it goes like this. Right? This is the general way it's written. Okay, so now this was a whole example of the whole thing. But now, step 4, what if we had an IVP? Which we will always have an IVP for these ones. Step 4, say that we were given because this will allow us to solve for C1, C2, right? Say we were given y naught is y of 0 is equal to negative 2, and y prime of 0 is equal to negative 2. Did I copy that down wrong? Hold on. I believe this is supposed to be a 3. Okay, so if we do this, if we plug this back into our general solution. Well, first of all, let's do this. Let's solve for y prime first, because we're going to need it. So this would be negative 3 c1 e to the negative 3t plus, minus 4 c2 e to the negative 4t. Now we can do both of these. So if we do the first one here, y is negative 2. So we have negative 2 is equal to c1. If t is 0, right, then that's going to become c1 times 1. Because remember, e to the 0 is 1. I'll write it out for this first one. Plus c2 e to the 0, right, which is also just 1. Now, prime, so we have 3 equals, that's negative 3 c1 minus 4 c2. Now, I just want to show you another method of solving, because we just learned about determinants, right? We just used the Wronskian, we used a determinant. I just want to show you another way that you can actually solve for C1 and C2. Let me just rewrite this so it looks nice. I'm going to show you another method. So this method is called Cramers Rule. Cramers Rule later on is going to become very, very useful to solve. It makes solving like substitution problems much faster. When we get into like variation of parameters, which is coming up very soon, those problems are very long and the substitution is very long. So using Cramers Rule saves a lot of time. So I think it's best that you at least look at it now and maybe use it for like 1 or 2 problems. But I will say, for these problems, it probably is faster just to do substitution or elimination. But I just want to show Cramers Rule. So let's look at Cramers Rule. So if you've taken matrices before, you know that if we have C1 plus C2 is equal to negative 2, and we have two, 3, right? So if we have this can be rewritten as, if we write it out in augmented matrix. So what that means is you can write a systems of equations. It's the same exact thing. All I'm doing is writing it down in a different way. This bar here means like equals to. So this is just like a coefficient matrix. You're writing down the coefficients of our terms. This is for C1, this is for C2, right? So if you've taken linear algebra matrices before, you should be familiar with this. My textbook actually goes over this Cramers Rule in this section. That's why I really want to cover it, because it's very useful for later on. Okay, so, and I'll show you substitution as well after it, just in case you're confused. So now what we're going to do, so let me look at the formula for Cramers Rule. Let me find it here. So the way the formula for Cramers Rule goes, let me write this out. 1, 1, negative 3, negative 4. Oh, sorry. Let me write it like this. If we have something like this, A, B, C, D, and this is E and F. Cramers Rule, so what you can do here, okay, so typically this can be rewritten as follows. This is the same exact thing. I just rewrote it. So if excuse me. So this is basically, I should rewrite. I shouldn't label that. This should be like C1, C2. Yeah. So all I did was rewrite this. Like this is our C1 row, this is our C2 row. Anyways, so if this is the case, because this works like this, because when you multiply a matrix, you don't multiply it directly across like this. Like this and this isn't C1. It gets multiplied by you go like this. You look at this first row here and this one here, and you multiply it like this. So you do A with C1 and B with C2. So you think of flipping the A and the B, right? And then multiplying it by that. So that's where that C1, C2 column comes from over there. If you know how to multiply matrices together, then you know what I'm talking about. If not, that's okay. Just as long as you... Honestly, you can skip all this stuff and just stick with this. So as long as you got to here, what I'm about to show you next will make some sense. So the formula goes like this. If we're solving for C1, the formula is you're going to divide two determinants. You're going to divide by determinants. So it looks like this. So we're going to have E B over F D, the determinant, over the determinant of A B over C D. So this determinant, the one in the denominator, is just the left-hand side of our matrix, right? The rest of it is a little different, right? You do this box first, and then this one. But this box is backwards. See how we flip it? So it's a little weird. It's definitely some memorization for that part. But once you get the hang of it, it's pretty simple. And C2 would just be where is it? AE and CF. Over ABCD, which is also the same. See, the denominators for both are the same. It's the numerators that change. So for C2, we have AECF. So it's these two, the outside two. So it's a bit of memorization, I guess. There's other ways of memorizing it. Like if you're familiar with like if you like want to go on YouTube, find another video of someone deriving it, you can go ahead. I mean, you're not gonna want to derive it every time, but once you learn like the general formula for it and you get used to it and you rep it out, it'll save you so much time later on. So much time. So if we look at our system now, let me copy this. If we look at our system, let's follow this formula that we have here. So now remember, this is basically like saying AC1 plus BC1 is equal to -2, or is equal to E, which is -2. Here, so I'll do this. A, B, and this is E, right? We have -3C1 minus 4C2 is equal to 3. This is our E, this is our B, this is our F, this is our C, this is our D, right? And this is like our line here, right? So now let's write this out. So for C1, so let's do the denominators for both first. The denominators for both was just A, B, C, D, right? So for our coefficient A is 1, for B is 1, for C it's -3, and for D it's -4. For the numerator, remember it goes it goes these last two columns, but backwards. So that means we're going to go E and then B. So it's so E and then B. So we have -2, 1, right? I just looked at these two right here, and I go this way. Then we have 3, -4. Right? I just flipped these bottom two right here. Now for C2, remember it was the outside 2, right? So we have 1, -2, and -3, 3. Okay, so now if we do that, we can do this in our head, right? This determinant can be done in our head, so C1. So -2, remember, it goes this way and then this way. So -2 times -4 is 8 minus 3, right? Because when you do it the other way, you subtract. It's 8 minus 3 over, that's -4 plus 3. See how I got that? 1 times -4 is -4. And then you subtract 1 times -3, which is -3, but the minus is there, so it becomes plus 3. So then that gives us 5, 5 over -1, right? Yep, I have in my notes I made an error there, but yeah, this is correct here. So this would be what, -5? So then C2 is 1 times 3 is 3, minus -2 times -3 is 6. That's minus 6 over 1 times -4 is -4, minus 1 times -3 is -3 times a negative plus 3. So then that gives us -3 over -1, which is just 3. I seem to have my signs backwards here, unless my professor did it wrong. Yeah, I think my professor might have done it wrong. Because in my notes here, the signs are backwards, but yeah, he must have did his determinants backwards, I think. Alright, anyways, now we have our C1 and C2. We go back up to our general solution, which is up here. Y is equal to C1 e to the -3t. So y is equal to -5 e to the -3t. And then C2, C2 e to the -4t. And so this is our solution. So just a quick overview here. The first step is you propose x equals e to the rt to solve for y1 and y2. Then you take the Wronskian, which is basically just the determinant of the two solutions. And if the Wronskian is non-zero, then we have a fundamental set of solutions, right? That's what we found. Step 3, we can write down our general solution. And step 4, you solve the IVP. Now, I'm going to take something from my textbook, and I'll be right back. Okay, so there's just one more thing I want to go over really quick for this section. So there's times, actually, let me just show you. So here, there's going to be some times where, if you look at this section right here, it says using the theorem 3.25, which is what I copied over here. See, they give us a T naught, right? They give us T naught, but they don't give us these though, right? So if if you're ever doing these problems here, you have to actually you have to actually solve for two different general solutions, y1 and y2. And this is different from those other two solutions. So you're going to use two initial conditions. You're going to get your general solution, right? Like we had before. We're going to get our initial general solution, which is this right here. And then you're going to have to do two, either Cramers Rule, substitution, elimination, whatever. But you're going to have to solve for C1, C2 two times for both sets of initial conditions. This one's for one general solution. This one's for the other general solution. So just be aware of that. I'm going to do one of these examples in the next video. But I just want to wrap up this one. I just wanted to show the general overview, and then the next video I'm just going to do a whole bunch of examples from the textbook, all right? Okay.